Hello students, welcome to week 1 of CS3102. This week we're mostly going to be discussing some background material from discrete math, and then we're going to be transitioning into some foundational material for this course. One of the most important skills that we're going to be using this semester are those of problem solving and how to present arguments or proofs. Hopefully you develop these a little bit in your discrete math course. We don't expect you to be experts by any means, but we will be building upon those throughout the semester. What we're going to be talking about today, first of all, is how we can approach new problems that we haven't seen before, and also how we could take solutions for those new problems and present them compellingly. So I have this problem. I have this stack of pancakes, but I have the largest pancake on top. That means if I tried to drizzle syrup all over this stack, only that top pancake would actually receive any syrup. So in order to have this stack sort of properly ordered, I need to have the largest pancake on the bottom, the smallest pancake on the top, and all the other pancakes in order in between. Now the problem is that when I try to rearrange the stack of pancakes, all I'm going to be able to do is insert my spatula somewhere in the middle of this stack, and then flip everything that's above the spatula. So I need to figure out how can I, by just doing these spatula insert, flip actions, get my stack of pancakes from largest on the bottom to smallest on the top. So one of the best ways to start approaching a new problem is to actually work out some examples. Now, I don't actually expect you to make pancakes in order to try this out at home. So instead, what we're going to do is we're going to develop some sort of notation so we can represent this problem without actually needing to make these pancakes. So the way that we're going to do that is, as you can see that I've done here, we're actually going to label all of the pancakes with numbers, where 1 is going to be the smallest pancake, and then 2 is going to be the next smallest after that, and then 3 is the next smallest from there, and then we'll have 4 is the next one from there, with 5 being the largest pancake. So now that we have a good notation to use, we can do lots of examples, and we don't need these anymore. So back in the kitchen, we labeled each of the pancakes according to their size, where 5 was going to be the largest pancake, 4 the next largest, down to 3, 2, and then 1 is the smallest. So now we know how to represent pancakes. Let's figure out how to represent our stack of pancakes. So let's consider, for instance, what we might want the sorted stack to look like. So for our sorted stack of pancakes, we probably wanted 5 at the bottom, and then 4 on top of that, followed by 3, and then 2, and then 1 at the very top of that stack. So this is going to represent a sorted stack of pancakes. Now, because English speakers typically write things horizontally rather than vertically, it's probably going to be a little bit more convenient for typing and such if we sort of rotate this stack 90 degrees, so that this stack, 1 on top, then 2, then 3, then 4, then 5, that we can represent as instead maybe 1, 2, 3, 4, and then 5. So now we have this notation for how we can represent any stack of pancakes using just some regular writing. This is going to make things a lot easier as we work through examples in a moment. The one thing that we have left to consider now is we've represented a stack. How can we think about what flipping a stack of pancakes looks like for this representation? So over here, we had our stack 1, 2, 3, 4, 5. And let's say that we wanted to flip the top 3 pancakes. That is, I want to insert my spatula between pancakes 3 and 4, and then I'm going to flip everything above that. So when we flip the top of this stack, that's going to invert the order of all of those pancakes on the top. So everything, invert the order of all the pancakes above the spatula. So this will become 3, 2, 1. And so if we compare that to what our notation suggests, that says that we're going to be inverting everything before the 3 to be 3, 2, 1. So now we can see that the types of sort of manipulations that we're allowed to do with this notation we have on the right are the ability to flip kind of any prefix of this sequence. So we can transform with one flip, maybe the sequence 3, 2, 1, 4, 5. So let's say that I had my stack of pancakes look like this. If I were to flip the prefix of 3, 2, 1 in this stack, that would transform that to my sorted prefix in 1, 2, 3, 4, 5. So this stack can definitely be sorted in just a single flip. So next I would recommend that you work through some of these examples for yourself. Just come up with sequences of pancakes 1 through 5 and see if those can be sorted. Please pause the video here and try to work through some examples on your own. While you're working through these examples, ask yourselves these questions. Do you notice any patterns or general rules about this problem? Were there any sequences you came across that you were unable to sort? And if not, then can you identify some sort of general strategy that you can always use to sort any stack of pancakes? This is sort of the observation that I made, which is that in order to get a pancake onto the bottom of the stack, you're going to have to first move it to the top of the stack. So what I mean by this is that if we had some sort of stack of pancakes, for instance, let's say 3, 2, 5, 1, 4, for instance, certainly to get this stack sorted, we're going to need to eventually get the pancake numbered 5, so that biggest pancake needs to eventually get to the bottom of the stack. Now, in order for us to get it there, at some point, pancake 5 is going to have to end up on the top of the stack, because then that's the only way we're going to be able to flip the entire stack over to end up with 5 at the bottom. So if we want 5 on the bottom of the stack, then at some point we're going to have to get 5 at the top. For instance, by inserting the spatula between 5 and 1, we could get to 5, 2, 3, 1, 4, and then finally get 5 to the bottom of the stack by inverting the whole thing to get 4, 1, 3, 2, 5. So this is what I'm going to consider kind of the gold star observation about this problem. That in order to get some pancake to the bottom of the stack, it must first be at the top of the stack. So let's consider the stack 5, 2, 3, 4, 1. I'm going to claim that this stack requires 4 flips to sort. So what we've done so far is we've sort of identified our problem. We figured out ways to write down our problem and play with examples of them. And we've made some observations about how the problem behaves. And next what we're going to do is we're going to take what we learned through that process in order to actually write proofs about this problem. So the proof that we're going to write is that this stack of pancakes, 5, 2, 3, 1, 4, requires exactly 4 flips to sort. That is, in order to show that it requires 4 flips to sort, we kind of need to show 2 things. We first need to show it's possible to sort in 4 flips. And we also need to show that it's not possible to sort in less than 4 flips. So if we can show both of these 2 things, then we're actually showing that sorting this stack of pancakes in the fastest way possible is going to take exactly 4 flips. So for a moment, consider how you might approach these two arguments. How might you show that it is possible to sort a stack of pancakes, or this stack of pancakes, in 4 flips? And how might you show that it can't be done in fewer than 4 flips? Pause here and consider how you might approach each problem, and also think about which one of these is actually going to be a more difficult thing to demonstrate. Many of the arguments that we're going to make in this class are going to fit into one of 2 categories. Typically, we're going to see that proofs that we make are either going to be existence proofs, which are going to be the sorts of arguments where we're trying to show that something does exist, and then other times we're going to see these non-existence proofs. And this is the sort of argument where we're trying to show that something does not exist. So as an example of an existence proof, consider that I wanted to demonstrate that I am a millionaire. So provided that I am a millionaire, it's going to be not so difficult for me to prove that to somebody. For instance, I could show somebody my bank account and show that there's over $1 million in there, or show someone my stock portfolio and show that that's worth over $1 million, or show that I've got some sort of really fancy house and the market value is over $1 million, or something like that. So demonstrating that I am a millionaire is not too difficult. However, by comparison, if I wanted to prove to you that I was not a millionaire, that's going to be way more difficult to do. So for instance, if I showed you my bank account and there were only $3 in that bank account, then how do you know that I don't have a stock portfolio that has over $1 million in it? But if I showed you my bank account and my stock portfolio, and I showed you this rundown shack in the woods that I live in, then how do you know that under that shack in the woods there isn't some sort of buried treasure that's got over $1 million worth of gold? So it's just going to be really difficult for me to prove conclusively to you that I am not a millionaire. So when we look at these sorts of proofs, these 2 categories of proofs, existence proofs, these are typically, we're going to say, relatively easy as compared to these non-existence proofs that are going to be fairly difficult. So we might as well start with the easy ones. Let's start with this upper bound proof. So to do this, all we need to do is find a way to sort this stack of pancakes in 4 flips. So what we can do is just say 5, 2, 3, 4, 1. Well, 5 is on the top, we need it to be on the bottom. So let's invert the whole stack. So that'll get us to 1, 4, 3, 2, 5. And then next, maybe what we can do is insert our spatula between 2 and 5. And then that's going to get us to 2, 3, 4, 1. Sorry, 5 at the very end. And then if we put the spatula between the 4 and the 1, that's going to get us to 4, 3, 2, 1, 5. And now you can see that everything above the 5 is in reverse sorted order. So if I put my spatula between the 1 and the 5, then I'll end up with 1, 2, 3, 4, 5. I have a sorted stack of pancakes, and I did that in 1, 2, 3, 4 flips. So our upper bound proof is done. Now for our lower bound proof, we need to show that it's not possible to sort in less than 4 flips. So there's a couple of ways that you might think to do this. So perhaps the first way you would try is you could, for instance, attempt every sequence of 4 flips and show that none of them are going to end up sorting your stack of pancakes. So that would certainly work if you were to do literally every single sequence and show that none of them resulted in a sorted stack. Then your proof would be complete. But that's going to be pretty tedious. And in fact, further on in this course, we're going to see that sometimes with these non-existence proofs, there might be an infinite number of potential options, and we're certainly not going to try to enumerate all infinite possibilities. So let's do something that's going to be a little bit shorter and more generalizable than this strategy. The strategy that we're going to use is a proof strategy that we call a proof by contradiction. Contradiction is probably the most common strategy for doing these non-existence proofs. And the idea of a proof by contradiction is that you're going to assume the opposite of your claim and show that you can conclude something that is untrue from that. So for this proof by contradiction, what we're going to do is we're going to say, assume toward a contradiction, there we go. So assume toward a contradiction that we can sort 5, 2, 3, 4, 1 in less than 4 flips. That is, there's a way that we can do it in fewer than 3 flips. Or in fewer than 4 flips, so 3 or fewer flips. What we're going to do is we're going to show that this assumption that this is possible is going to allow us to conclude something that is just totally untrue. So in order to demonstrate this, we're going to use our golden rule. So our gold star rule for this problem was that to get a pancake to the bottom, it must previously have been on the top. So we definitely know that in order to have a sorted stack of pancakes, 5 needs to end up on the bottom. So that means that by the time we got to our third flip, so after the third flip, so after this third flip, we definitely know that 5 must be on the bottom to sort in 3 flips. Which means that after the second flip, because of our gold star rule, 5 must be on the top. So what we're going to see then is that because of these two, the only hope we possibly have of sorting this list in fewer than 4 flips is if our first flip is going to put 5 on the very bottom. Because if, after the first flip, five was in the middle, then since after the second flip, 5 must have been on the top, basically this flip here just undoes the first flip. So the second flip is just going to undo the first flip in this case. Because what we needed was we needed 5 to be on the bottom by the end of flip 3. So if 5 was in the middle at the end of flip 1, then in order to be at the bottom by the third flip, it needs to be at the top after the second flip. So if flip 1 it's in the middle, then flip 2 we need to just simply undo that and move that back to the top so that it can be on the bottom, which means that this sequence of 3 flips is just doing the same as inverting our stack of pancakes, which we know isn't sorted. So now our first conclusion, so if we can sort this stack of pancakes in fewer than 4 flips, then we know that the first flip must invert the whole stack. So now we know that after the first flip, we go from 5, 2, 3, 4, 1, invert the whole thing, and we're going to go to 1, 4, 3, 2, 5. So what we're going to see next is that since the first flip puts 5 on the bottom, what we need to be able to do to sort the entire stack is we need to be able to sort those first 4. So if we can sort 5, 2, 3, 4, 1 in fewer than 4 flips, then it must be that we can sort 1, 4, 3, 2 in fewer than 3 flips. So we need to show, so what we're going to need to do is we need to sort 1, 4, 3, 2 in less than 3 flips. If we think back, though, to our gold star rule, in order to sort 1, 4, 3, 2, we need to get 4 on the bottom. So that means by the end of our second flip, we need 4 on the bottom. So 4 must be on the bottom. Which means that after our first flip, we put 4 on top, which essentially forces us to say that the first flip is going to insert the spatula between 4 and 3 to give us 4, 1, 3, 2. And then our second flip, to have any hope of sorting things, is going to need to invert the whole stack, which is going to be 2, 3, 1, 4. And now we're out of flips, and this is not sorted. We can see here that it is impossible to sort 1, 4, 3, 2 in fewer than 3 steps. So our assumption up here towards a contradiction was that 5, 2, 3, 4, 1 could be done in 4 flips. But if 5, 2, 3, 4, 1 could be sorted in fewer than 4 flips, then it must have been that 1, 4, 3, 2 must have been sortable in fewer than 3 flips, which is impossible. So our original assumption that we could sort 5, 2, 3, 4, 1 in fewer than 4 flips must have been incorrect. And so that is impossible. So now we have shown both the upper bound portion of this and the lower bound portion. So now we know that 4 flips is the best we can do for our stack of pancakes. This video is intended to give you an example of how to go from problem description to proofs about that problem. I have a few general tips for how to go about this process. When first approaching a new problem, the first thing to do is to make sure you understand what the problem is asking. If you're not certain you follow, then please ask a cohort mate or post something to Discord for clarification. Next, if necessary, you should come up with a good notation for how to write down instances of that problem. Usually we'll be providing the standard notation for you, but this won't always be the case. At this point, you'll have everything that you need to work out some examples. So try some examples and keep trying until you develop an intuition for this problem while trying to identify certain patterns or rules that this problem follows. It's generally a good idea to look at some special cases while you're doing this. For instance, what happens if the problem is of size 0 or of size 1? And finally, apply that intuition that you developed through those examples to solve that problem at hand. And once you've solved your problem, it's time to write a proof for that. So a proof is really just an essay that takes a reader step by step through an argument where each step is obvious from the previous steps. And the meaning of obvious here is going to change depending on who your intended audience is. For this class, your steps should be obvious to, let's say, the typical student who has finished discrete math. In other words, you at the start of this semester. Now, I caution you while you're building these steps not to confuse obvious and intuitive. So to say something is obvious means the justification is going to immediately come to mind for somebody. To say that something intuitive, though, typically comes as a substitution for justification, and oftentimes your intuition is going to lead you astray. Now, when you're writing your proofs, make sure you introduce the strategy that you're going to be using and also give the idea for how that strategy is going to be applied. So your proofs should be intended to teach someone something, not surprise or impress them. Once you've written your proof now, go ahead and tie everything together and summarize how your conclusion followed from your argument. Happy proving!